For many, AI success isn't limited to how many GPUs you can buy. It's limited by how fast those GPUs can talk to each other without tripping over the plumbing. The network. It can be the unsung hero or chief villain of your AI journey. Today, two of WWT's top networking minds, Justin Van Schaik and Eric Fairfield, lay out the real choke points slowing AI projects to a crawl. Things like bad multipathing, tail latency spikes, and reliability gaps that turn training jobs into week-long sagas. They'll also explain why next-gen Ethernet, not exotic accelerators, is quietly rewriting the rulebook for scaling AI. By the end of this episode, you'll hear why the fastest path to AI value might not start with another GPU purchase, but with a ruthless look at the wires, switches, and software stitching it all together. This is the AI Proving Ground podcast from Worldwide Technology. Everything AI, all in one place. Let's get to it. Justin, Eric, thanks so much for joining us today on the AI Proving Ground podcast. How are you?
Doing great.
Fantastic.
Excellent. Well, let's dive in. Justin, we hear a lot about GPUs, accelerators, and that kind of being, what drives AI progress. Tell me why it's the network or networks and not GPUs that are that AI choke point for organizations that might be stumbling or stalling on their AI journeys.
So, I'm going to give you a sub-slice of that then. The network there's always a moving bottleneck. Something is always going to be the fastest part and something's going to be the slowest part. The challenge has been with AI, you have to get the GPUs collectively speaking to each other. And that collective action requires a lot of very high bandwidth, very low latency interconnectivity. Historically, any kind of flaw in the transport, in the network, retransmits, dying transceivers, slow things like that, tend to have a inordinate impact. A 1 to 2% fail rate of transceivers can have a 60% impact on the job completion time for a generative training run. So that's what we've been dealing with historically. We're just stepping through and trying to fix it every step of the way.
Yeah, and real quick, I'll jump to you here, Eric. But first, Justin, why is that? You mentioned how GPUs need to talk collectively. Why do they need to talk collectively before they move forward?
I'll use the human brain analogy. One brain cell ain't that smart. You have to have, we have to have a few trillion. You have to have a few 100,000 neurons interconnected to make a really powerful neural network that can solve these problems. One large monolithic GPU is not going to cover anything. You have to have several thousand working together. And that's where the collective works in.
Yeah, no, absolutely. Eric, this is going to be a dumb question by design, but why can't we just plug these GPUs or plug AI, so to speak, into the same network that email runs on, or any other enterprise application for that matter?
Well, as Justin alluded to, these GPUs, they talk to each other collectively, and they have to come to an agreement within a very specific time frame to be performant. And you don't want these GPUs having to contend with traditional traffic, right? Email, web surfing, March Madness, all those kinds of things, right? You don't want to have to contend with that traffic. Otherwise, it's going to affect the job completion time very significantly.
Yeah, anything impacting that communication does have a huge impact, like you just said. Like, to use a basic analogy, these things are essentially doing very high-dimensional math. So, but they're breaking up in chunks. So, for example, if they all say, okay, we've multiplied X by Y, now we need to carry the 7. Who has the 7? Oh, crap, find the GPU with the 7. He's running a little bit slower. You wait until the 7 shows up before somebody can carry that 7. That's a very dumbed down, concept of it, but that's essentially what's happening. Any impact to any GPU that slows down anything will slow the whole process.
Yeah. And how have networks then evolved over just the last couple of years, or 3 or 4 years, as generative AI has jumped onto the scene? What types of changes have really been made in terms of networking that have allowed to enable that communication, that fast communication?
I would say probably one of the biggest things is bandwidth has been changing very frequently, right? It was just a few years ago when we were in shock that we're doing 100 gig in our data centers. Now the data center, the GPU networks are 400 gig. We're moving to 800 gig, and 1.6 terabit is in the very near future here. So the amount of bandwidth that's being utilized is it's amazing how that's changed, and how Ethernet is having to change as a protocol. This is something Justin's been very involved with, is Ultra Ethernet, right? And how Ethernet's going to change its way of communicating to overcome some of the historic challenges of congestion management.
Yeah, I do want to get into Ethernet and Ultra Ethernet, but just real quick, you mentioned how the needs are constantly rising. Eric, is it a sustainable path forward where we're going to be able to account for all that moving forward?
I would say it's definitely sustainable, but what people have to take into consideration is, as we're getting faster, the fiber needs are going to change. So there's going to be a distinct transition from our typical one pair of fiber to using cables like MPO12, MPO16 cables to transfer that much data. And really, even moving from multi-mode fiber to single mode fiber, we're seeing this with 800 and 1.6 terabit is the movement towards single mode fiber. So it's sustainable. It's just we have to change the way that we're looking at our cabling structure, which is also going to work hand in hand with power and cooling delivery. Those are probably the biggest sustainability challenges right now, is actually the power and cooling more so than the network.
Exactly. Well, there's always going to be that moving target, but as we start to, essentially one of the old rules of networking is no matter how much bandwidth you put out there, something will consume it. And as we put, yes, we have a sustainable growth path for the actual bandwidth. Latency is about as low as it can get. Reliability has been vastly improving, and that's also what Ultra Ethernet is talking about. But we've been seeing Ethernet, modify itself many times over the years. And it's like we used to have, like I use voice over IP as a common analogy. When they first had voice over IP, we had PBXs, and that was how you did your phones. And then eventually they said we can do voice over IP, but you have to have an entirely separate Ethernet network to run this. You can't converge it because it's very sensitive, and Ethernet will drop every pack, and it's going to be horrible. And then eventually we figured out how to do the QoS properly. We figured out how to have the right bandwidth, all the proper adjustments. Now VoIP is ubiquitous. Ethernet evolves. The requirements that we're seeing in here are in one sense, just an iteration, the next iteration of every bit of growth we've had to deal with in networking. And in another sense, some of the peculiarities of why they're actually going into the Ultra Ethernet Consortium to deep dive into some really granular aspects of the transport for AI that needs to be updated, needs to change. And that's irrespective of whether you're running on Ethernet or InfiniBand, some stuff has to be modified.
Yeah, Justin, give us a little bit of that. Maybe dive a smidge deeper with the Ethernet, the InfiniBand, now Ultra Ethernet. It feels like we're adding to it every so often. So give us the lay of the land when it comes to at least those three solutions and anything else that might be coming down the line.
If you look at it, the transport protocol itself is almost, as long as it delivers the requirements, you don't care what it is. So if you look at the AI as an application, just like we say voice is just an application. AI is Skynet.exe. And as long as you have the proper, you deliver what it needs, it doesn't care how you're delivering it. InfiniBand can do it. Ethernet can do it now. And we're moving into the Ultra Ethernet where it's addressing those very specific problems, such as those retransmits when something drops. Currently, so the go fast juice that actually makes Ethernet or InfiniBand really, really fast is RDMA, remote direct memory access. And what that does is allow you one machine to put directly resident in the memory of another machine information without having it checked. similar to what we saw with acceleration with X.25 to frame relay. It said, we now trust the transport. We're just going to send it straight through. RDMA has always been very, very twitchy. One of the worst parts about it is if you drop anything in sequence in RDMA, it does a go back N. So it rolls back to the last known good, which means that any kind of successive retransmissions or glitchy things, one drop packet per every session can actually have a huge outsized impact on the job completion time. So the RDMA itself is being rewritten in Ultra Ethernet. Not like, the trash, not throwing out the baby with the bathwater, but they are looking at things like granular retransmits. So it only, says, you dropped, packet 7 out of 10. Please retransmit packet 7 instead of, let's go back to 0 and go through the whole thing again. There's a lot of other tweaks that are going into there. Retransmits in IP-based networks have traditionally been, handled at the transport layer. They're moving all that down to the link level. So it's actually happening in hardware now instead of in a software retransmit. There's no CPU interrupt to make that happen again. It's not even going into a TCP offload engine. It is just hitting directly. So, and then there's a lot of other things in there. Quality of service. Instead of prioritize, so in a large elephant flow for in generative AI, you're going to have, like, it's a lot, it's highly varied. It's not a homogeneous stream. Not every packet has to be delivered reliably. So now I can actually categorize into sub-levels. Am I going to be doing, reliable ordered delivery, reliable unordered delivery, all these things, unreliable, unordered. It essentially can classify every single, packet in a workflow so that only the stuff that needs the highest priority will get sent that way. That frees us up a lot because then we suddenly don't have to have every part of a flow between 2 GPUs or between 1,000 GPUs or 10,000 GPUs won't be prioritized the same. Gives us a lot more leeway in what can and can't be done.
And is that just enabling speed, or is it avoiding or mitigating some of those ripple effects that you mentioned earlier if something is not delivered reliably, or what's the benefit of that?
So let's roll back to the RDMA again really fast. If you look at a day in the life of a packet, which is, the network crawl between, sent from point A to point B, we don't look at it from NIC to NIC anymore. We look at that process in terms of from GPU to GPU, which is, so you can have 2 8-byte registers go into a GPU, 1 8-byte register will come out. That is a 64-bit flop. Now that goes out to the L1 cache, L2 cache, L3 cache, onto the PCI bus, over to the NIC, gets checked for everything along the way, and then finally hits the wire. RDMA removes all of that error checking and just sends it right out to the wire. And then on the other side, the other GPU does the exact same thing going back up the stack. So what you're doing here is not necessarily creating more bandwidth out of it, not necessarily creating a lower latency out of it in terms of the speed of light is still the speed of light. We are minimizing the number of touches, the number of steps that we have to do in the middle in order to make sure it happens. So it's a question of efficiency, if you will, more than just throwing more scale per scale out at the problem. Does that make sense?
Yeah, no, absolutely. Eric, anything you would build on top of that, or where do you see the delineation between, Ethernet, Ultra Ethernet, InfiniBand, and how does that affect our clients or enterprise IT teams? Do you have to, pick one and stay in that lane for a long time, or can you bounce back and forth, or can you even use a best of breed type of situation?
So that is a fantastic question because we get this all the time, Ethernet or InfiniBand. What's the best way to look at this? And there's a few things that we always have to keep in mind. And one of them is, how well do you know InfiniBand? There's a lot of customers that have deployed InfiniBand that really have challenges operationally because they don't have anyone that really knows the ins and outs of InfiniBand, how to troubleshoot it. InfiniBand, actually installing it, very, very easy. It's very plug and play, but it goes off the rails when it comes to problems, right? As soon as you have that problem and you don't know how to troubleshoot it, now you have to call the experts. Who are you going to call? There aren't a lot of InfiniBand experts out there, and the ones that are out there are rather busy dealing with other implementations, troubleshoot, stuff like that. So really you have to look at is Ethernet good enough? And that's something that we have shown in the AI proving ground time and time again now, is in a lot of small networks, um, we're able to deploy Ethernet, and it's just as performant, if not more performant than InfiniBand, right? And a network engineer can go in and troubleshoot it because they already understand Ethernet operationally. So that's one of the biggest things we look at is, what's your operational model? Can you even handle InfiniBand for when it goes sideways?
Yeah, Eric, how is the need or rise of distributed architectures? How is that compounding the fact even more, or is it?
If by distributed you mean, kind of the calico tapestry of networking, that's not necessarily going to be happening a whole lot with AI networks. They kind of require homogeneous transport. You're not going to be going from, 100 gig to 10 gig to 400 gig to different QoSs. Like it requires a fairly homogeneous island of communication. You can connect that in with the rest of the network, but not at a spot where it's going to be sharing any kind of traffic with the AI itself.
Yeah, what we are seeing is, when it comes to distributed architecture, some of that will come down to edge AI solutions, right? Where the GPU is integrated as part of an edge product or an edge application, and it's not part of an overall AI training network or an inferencing network. It's a very point solution, that has this intelligence at the edge, because the performance needs to happen at that location instead of coming back to a data center sharing with something collectively, right? So there is distributed nature within AI for very specific use cases.
This episode is supported by Nokia. Nokia helps you realize your digital potential with trusted purpose-built IP, optical, fixed, and data center solutions, providing superior performance, security, and seamlessly integrating into any ecosystem. Nokia, pioneering networks that sense, think, and act.
Justin, I am curious. At least as of this recording, we just got out, or relatively speaking, out of Cisco Live, and we've had a bunch of other conferences and NVIDIA GTC, etc. Tell me more about this partnership that I'm hearing up between NVIDIA and Cisco to bring Cisco's networking and operating systems to NVIDIA's Spectrum X ecosystem. What does that all signal to the industry?
So in terms of like industry patterns, it's the best of both worlds. Just to be perfectly candid here, a lot of the industry has been absolutely flocking to NVIDIA's solutions because they're excellent, they're fast, and they're powerful. But they're also the only solution on the market. And they have a tightly integrated vertical stack, and everything works together. Many of our customers, many customers in the industry are looking to have some level of diversified risk around those suppliers. And if it's one great supplier for GPUs, they don't want to have that same great supplier for network. So integrating Cisco into it gives them choice as well. Under the hood, what we're hoping to see is some level of standardization on the best way to do it. Currently, there's several thoughts around it. At the end of the day, it's where do you want to reorder your packets? If you're going to use all of your bandwidth, you can spray them out across the environment. There's going to be out of order delivery. It still has to be delivered in order to that GPU on the other side. That's the RDMA way of things. If it's not out of order, things go wrong. So you reorder it either inside the network, or you reorder it at the edge on like a DPU or a Bluefield or something, or ConnectX-7 or SuperNIC. And various partners have various methods for doing it. Cisco has one way, NVIDIA has another, Broadcom has another, Arista has another, Juniper has a different one also. We are hoping to see, by combining some level of engineering expertise between these major vendors, that they'll start to come up with a best option with other options available. Cisco uses a DLB, NVIDIA uses Spectrum X. By the first stage is just allowing Cisco Nexus to participate in that environment, meaning at layer 2, there's going to be a handshake between the SuperNIC and the switch in the middle that says, you are a Spectrum X compatible switch, therefore I will use you. That's the NVIDIA side. And then on the Cisco side, they just have to use some P4 programmability on the Silicon One chips to allow it to speak Spectrum X, meaning will it do adaptive routing in the middle? Will it have some kind of congestion metering available as well? All these things are being factored in. So we're very excited about where it's going. Hopeful that it will deliver everything it was expected. But of course, strike that comment. Of course, they're going to be doing deliver what's expected.
Yeah, to add on that, I always look at it. One of the things that NVIDIA used a lot was adaptive routing is what helped drive InfiniBand, the use of adaptive routing and Sharp together. And really what the Spectrum X architecture is doing is they're taking those capabilities from InfiniBand and really applying it to the Ethernet world. So they've had that special sauce. And a lot of the other Ethernet vendors really didn't have a special sauce outside of implementing things like ECMP entropy tools, like Justin mentioned, DLB, dynamic load balancing, or something we call flowlet switching, packet spraying. There's a variety of ways around that. And I wrote a whole article around ECMP. And now Cisco, in this relationship, has brought a special sauce to their solution, right? By being able to tie into the NVIDIA adaptive routing architecture. So again, it's very exciting to see where this is going to take it, because this will give us the ability to look at Cisco in NVIDIA reference architectures as well. So very exciting.
And maybe dive in a little bit deeper, Eric, on why that's exciting, and more so, like, why is that exciting for enterprise IT teams?
Well, again, if we talk about some of the operational models that are out there, you have a lot of organizations that have standardized on Cisco switching, right? And by Cisco having this partnership with NVIDIA, they're going to be able to get into the NCP program for helping build reference architecture. So for a customer, they can now implement these AI networks with Cisco solutions, knowing that they're designed and accepted by NVIDIA, and they don't feel like they're having to go rogue, right? So again, it's going to allow us to tie into existing operational models and not have to worry about, do we have to convince them of moving necessarily to a different switching platform to support this?
And not just a different platform, but simplest terms, like, let's think it's a different operating system.
Yeah.
Like, it doesn't really matter where you're standardized, but there's a huge pushback, and there's a lot of institutional and technical inertia associated with bringing in an entirely different operating system. So a lot of customers are very happy with their Cisco and their CLIs. They do not want to actually start incorporating Cumulus or Sonic into the environment. It just complicates things. So this allows them to actually port their same data center-wide and enterprise-wide skill sets directly into the AI without having to go through that sharp learning curve. Now it's just another protocol to learn, a few more tweaks, special environment sort of thing, much more easily absorbed into their operating models.
Yeah, Justin, a couple months ago, or it might have even been back in 2024, you wrote in an article that, and you used a line that I really liked. You had a quote unquote science that needs to be verified. These systems need to be tested on real data that are bouncing between real servers and GPUs or storage or whatever it might be. You're talking again about, having a new OS, new operating system. How would our clients, or any organization for that matter, start to verify that these systems would work within their own real world settings?
So it's a scientific method. First, you define the problem. They have to define what they're trying to accomplish. Then you gather the information, you form a working theory like, hey, you know what? Ethernet will work great. We need Ultra Ethernet, or we need to run on Nexus, or we need to run wherever else. And then you test it. The testing part has been the biggest challenge in the industry, really, because there is such a complex ecosystem with a lot of very expensive hardware. And if you're going to make a $10 million, $100 million investment in a full-on AI architecture, you want to understand how it's going to perform before you can do it. And that's why we actually built the AI Proving Ground. And that's a lot of the work that we have coming in is we want to see if what we think will happen. Hence, science that needs to be verified.
Yeah, I like that you mentioned the AI Proving Ground here, certainly the namesake for our podcast. Eric, can you explain a little bit better in terms of what the AI Proving Ground is and what it offers clients or organizations out there as it relates to testing, validating, and proving out that they're on the right path for the AI journeys?
Absolutely. The AI Proving Ground really gives a customer the ability to bring their ideas to reality, right? How can we test building out an AI system, be it hardware, software, right? And make this a reality to see if we can even do this, right? How can we make the art of the possible happen? And what architecture is going to work best? Do we need to look at InfiniBand versus Ethernet? Do we need to look at Cisco versus Arista, right? What software is going to make the most sense? Do we run Slurm? Do we run AI, right? To do our orchestration. And the AI Proving Ground is the perfect place for them to do that because, one, we have the people to help build it, right? Because a lot of times the customers may not have the knowledge to do that. They don't have the lab. They don't have the budget to buy all this to see if it works even, right? And that's one of the biggest benefits of the AI Proving Ground is we have the people, we have the software, we have the resources, and the relationships with our OEMs to make the art of the possible happen.
And let's also look, time to delivery here, or because you look at the vast majority of our customers, they have excellent internal teams, a lot of intelligence. They've got their own labs, but the turnaround time on average is going to be like 6 months to a year to get hardware in, rack it, stack it, get it all going. We have this down to this is our focus, and we have this down to a martial art, so we can actually bring it in very quickly. So we can turn a 1-year evaluation cycle into a 3-month evaluation cycle. It helps them have the right information to make the right choices faster.
Well, that vendor ecosystem figures to get even more complex. Every networking OEM seems to be touting AI integrated offerings. How are you making sense, Justin, of the marketplace? Is it just going to continue to expand and expand and expand, or are we going to see some consolidation or partnerships by that way?
Bit of both. You're asking me to actually give you a prognostication of what the market's going to look like. We will see alliances, ongoing alliances happening between, say, Cisco and NVIDIA or similar kind of connections where they say we can collaborate on this. We'll see some fracturing as well. We'll see new entrants, AMD, starting to produce some good performance. We'll start to see, we've seen like with DeepSeek, there was a bit of a disruptor there as they came up with a less resource intensive, and more efficient way of processing. The numbers were still tweaked a little bit on when they published the data, but there's going to be disruptors that will change everything. There's going to be continuing alliances, and there's going to be people every once in a while, like we saw this happen with I'm bringing up the sordid past, but we had VCE between VMware and Cisco and EMC, and they fractured, and the entire integrated stack became a broken stack. We will be seeing those things happen as well. We try to stay on top of it by collaborating tightly with our partners. Also, keeping our fingers in the wind to see exactly what our customers are asking for. And we've had instances where what we've been hearing from our customers is significantly removed from what the strategic direction is of our partners. And that's where we talk to them and say, we are hearing different things than you are hearing. We should go through this.
Yeah, well, understanding that it's a relatively chaotic landscape and that, there's going to be changes in the market in the near term and long term. Eric, is there any advice or guidance that you would give to clients on how to handle that rapid pace of change? How should they look at the landscape and be able to, advance their organization forward, knowing that there could be changes coming down the line at any moment?
I think one of the most important things is really when we look at what we're doing, especially from an AI networking perspective, is when you're making choices, you have to look at the systems are going to change rather quickly. What was the new shiny object is going to have lost its luster after 18 months, 24 months very easily. But you have to think about, how does this play into the bigger picture? Because as the systems change, is it possible to reuse some of that architecture somewhere else? And this comes down to, a great example of the Ethernet versus InfiniBand argument is, as things change, can you put your InfiniBand network anywhere?
Now, you
No.
do file and print on InfiniBand? Probably not.
Exactly. So what you have to do is think, again, big pictures. As I go from, let's say, 400 gig to 800 gig, can I utilize this 400 gig in different areas of my network now? And those are the things that a lot of people don't think about is, when I make a decision about my high performance architecture, what do I need to do with it in 18 to 24 months? Is there a place for it somewhere else in the organization that makes sense, instead of just, a quick one-off?
Yeah, when it comes to the enterprise, you want to have a very much a top-down solution. It involves coordinated action at the C-suite level. You're going to be looking at the CFOs and looking at the CapEx and the OpEx, but at the same time, they have to understand that their standard depreciation cycles of 6 years, 7 years is not going to apply. They have to actually look at a 1 to 2 year refresh cycle consistently. So they have to bring it in to function flawlessly and be able to tear it down and tear it out also flawlessly. That's huge operational concerns. That's where the CEO has to be able to talk to the managing directors, has to be able to talk to everybody else. So it has to be very much a top-down solution. Customers who are doing a grassroots solution or historical data scientists sitting in a little small island of performance, very quickly it's become apparent that those do not scale. What did work has to change.
Yeah. Well, so far in this conversation, which has been fantastic, we've only necessarily talked about how the network can support or drive AI. I'm curious, let's flip that script here. Justin, where can AI really enhance and help accelerate or make more efficient the network? What types of use cases are we seeing in terms of applying AI to the network?
So, we've already seen a lot of machine learning inside networks. Put it at a full AI level, not certain, but we've had things where, security, where they do a, heuristic engine to actually look at patterns in the environment, learn the patterns of the environment, and then notice when something is outside of that norm, and then apply a fix. With varying levels of autonomy. They've had self-healing networks. They've had all things. So really bringing AI into the network is nothing new at all. As we've improved the capacity for this, we've also seen, we have a few other choices now. So I can have, other partners have their own little AI networking engines that'll run on a small L40S or something. And we can put that in. And then I can say things like natural voice interaction. I can say, hey Siri, what's my network look like today? And then the network will come and say, oh, well, blah, blah, blah. And it will tell you exactly where things are wrong, or please drill down into where that performance issue is. You're watching in real time. Brief me on it. It makes it easier to track down very complex environments and see where the problems are and how to fix them.
Yeah. Eric, any other AI use cases on the network that you foresee either, coming soon or maybe in the distant future?
I would say, the big thing is operational change, right? Again, how do we make it easier to troubleshoot something? How do we make it easier to manage the network? And I think one of the biggest things that it's going to drive is more appropriate data lake design, right? Where is the information? How can we access that information is really going to drive these different AI for network operations discussions, right? You already see it happening. Juniper with their Mist product has a fantastic AI agent built into it. Cisco, as recently announced at Cisco Live, they're looking to have an AI enablement across their entire platform, right? To make it easier to look at the network holistically. So that the big thing there, I think, is we're going to see better telemetry and observability data lakes occur, and that's going to be absolutely huge.
And that also pushes it out to the back to the edge again. Going back to that point, because if you look at again the data gravity, but having an edge compute where you have, I use cars as an example. Waymos, self-driving cars. Okay, they have to have certain level of autonomy. They can make decisions themselves, real time, based on the environmental inputs, and they do. But they also need to have some level of coordination with the mothership to ensure that they have the latest data. That could be either a dispatch to tell them where to go. It could be a real-time understanding of traffic patterns in the city so they know where to avoid congestion versus driving straight into it. And then, and then they have to worry about like backhauling their own data back to the mothership so that the data center actually has an updated understanding of what's going on. They also have to be able to function completely autonomously without a network. They have local city maps that they can actually continue to apply even when the connection goes down, so that they can still navigate the streets even if they don't have an understanding of the real time. So it's very collaborative, and AI will then help us analyze exactly what data has to live resident in that car. What data has to be easily fetchable, what data can wait for a couple of days. And it goes like that. There's the ultimate evolution of this, and is going to be something like I summon my Waymo to my house to pick me up to take me to work. The Waymo shows up and says, "Good morning, Justin. I see from your Fitbit that you did not sleep very well last night. I've taken the liberty of scheduling, ordering your favorite latte at Starbucks, and we're going to stop through for there. However, also it seems like your heart rate's a little bit elevated. Your cardiologist has suggested you don't deal with that. So we might cut back on, the extra shots of espresso today." But no, if you think about all that little conversation, there is a pre-existing HIPAA agreement. So it has to be able to pre-fetch. So when the car is being summoned to you, it has pre-fetched your actual medical data. It has accessed your Fitbit to see exactly where it's coming through. It has brought it all in, chewed it all up, and the car has a localized understanding as well as a more of a direction as to what to do with it. That's the Shangri-La, and yes, I know there's tons of ethical considerations around that level of integration. There's privacy concerns, but that's a theoretical kind of like, that's the art of the possible. And AI will help us determine, again, exactly how to make those decisions, where to put the data, how to move it faster.
Yeah, no, absolutely. That's fantastic. That's a great analogy. Well, we are running short on time, so I do want to cut it short here. Justin, Eric, thank you so much for taking time out of your day to join us on the AI Proving Ground podcast. Hopefully we'll have you back soon.
Woohoo!
Thank you
very
for
much.
having me.
All right, thanks again. Okay, thanks to Justin and Eric for sharing their time today. Today's episode highlighted 3 key areas. First, the bottleneck isn't silicone, it's the plumbing. All the H100s in the world can't save an AI workload stranded behind jittery links and tail latency spikes. So you need to first diagnose the flow of data and then decide whether to add more GPUs. Second, AI belongs inside the network, not just on top of it. From anomaly hunting security engines to conversational network copilots, embedding machine learning where packets live turns troubleshooting from a war room into a quick chat. And third, telemetry is the new gold. Rich, well-designed data lakes and the observability pipelines that feed them let ops teams shift from reacting to predicting, whether the endpoint is a data center switch or an autonomous car at the curb. The bottom line is, if you want AI that scales, start by asking how fast your GPUs can talk, not how fast they can think. The network is the heartbeat of every model you'll build next. If you like this episode of the AI Proving Ground podcast, please consider sharing with friends and colleagues and leave a rating or a review. And don't forget to subscribe on your favorite podcast platform or on WWT.com. This episode was co-produced by Naz Baker, Kara Kuhn, Mallory Shaffron, and Stephanie Hammond. Our audio and video engineer is John Knobloch. My name is Brian Felt. We'll see you next time.